Today we're going to look at mathematical induction, which is a vital component to our repertoire of proof techniques that's useful for many things that we do in algebra and actually throughout mathematics. And we're also going to apply that to a particular problem known as the division algorithm. So let's start with mathematical induction. And we need to take this actually as an axiom. We need to take that this principle works as an axiom. Now, once we see it, it will make a lot of sense, and that's why we take it as an axiom. And so axiom 8 is mathematical induction. I'm going to call this the standard version, because there's going to be another version that we look at that is called strong mathematical induction, even though it's equivalent to this one. But the standard mathematical induction can be stated in the following way. Let's let S be a set of integers. If two things happen. If, first of all, some number A is in S, and furthermore, whenever some number n is in S, we have that n plus 1 is in S, then S contains all numbers, all integers, greater than or equal to A. So let's think about what this says. We're starting off with a set of integers, and we're first saying that we know something's in it. We know A is in it. Showing that there exists some number that lies in the set. This is going to be what we call our base case. So whenever we do a proof using induction, we're always going to have a base case where we show that there is in fact something in our set. There's some number that satisfies whatever property we're talking about. And then we have to know that whenever some number is in S, some n is in S, then the next one has to be in S. And if those two things are true, then S contains all integers greater than or equal to A. So we can think about why this ought to be true. Well, from the base case, from part 1, we know that A belongs to S. Now, from part 2, which is known as the inductive step, so this implies, by the inductive step, that A plus 1 is in S. Because we know that whenever some number is in S, then that number plus 1 is in S. But if A plus 1 is in S, then we can use the inductive step again. So if A plus 1 is in S, then that means that A plus 1 plus 1, so A plus 2, has to be in S. But applying it again, that means that A plus 3 has to be in S, and so forth and so on. And so if you take any integer that's greater than A, greater than or equal to A, you can reach that number by applying the inductive step some finite number of times. And so every number greater than or equal to A has to belong to S. This is the basic principle of mathematical induction. Now, the way that we use mathematical induction to prove theorems has a pretty standard format to it. There's a pretty standard way in which we set things up. So let's look at an example. So let's prove that for any n greater than or equal to 1, we have that 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 divided by 2. Now, mathematical induction is not the only way to prove this fact, or even the most efficient one, but this is an excellent way of seeing how mathematical induction works, because it's a very straightforward application of it. So, when we do a proof by mathematical induction, we always have two parts that we need to prove, corresponding to the two parts of the axiom. First, we need to prove that some number actually satisfies the condition that we want. And that's the base case. Next, we have to show that if some number satisfies the condition that we want, then the next number, the next integer also satisfies that condition. So you'll notice that when we wrote down the axiom, we're talking about here S, a set of integers. Most of the time when we do problems involving mathematical induction, we don't explicitly write down what S is. We don't explicitly write this down in terms of a set. So let me go ahead and do this proof in sort of the standard way that it would normally be written down using induction, and then we'll go back and we'll see how exactly it matches up with the axiom as we wrote it using the set. So we've got two steps to this proof, and a lot of times we'll want to explicitly write it down. Base case, colon. Now, the place where we start is often determined by the statement of the proof that we want. We're trying to prove that, in this problem, that all numbers greater than or equal to 1 satisfy this condition, that 1 plus 2 plus 3, etc. up to n is n times n plus 1 over 2. Whatever the smallest integer that is that you're trying to prove the result for, that's your base case. So we could look at the situation, if n equals 1, then we need to see that this equation holds. Well, this equation would be 1 on the left-hand side because we're adding up all the numbers to n, but if n is 1, then we're just getting 1. And on the right-hand side, we have 1 times 1 plus 1 over 2. And those two are, in fact, equal. So what we've shown is that if we put n into the formula above, we get a true statement, we get a true equation. So the statement that we're trying to prove holds in the specific case that n equals 1, in the base case that n equals 1. So the base case holds. So now we go to the inductive step. So now we have to work in a little bit more of an abstract way. We have to assume that we know the result, that we know the formula that we're trying to prove for a specific value of n, but without saying what that n is, just for n, and prove that it has to hold for n plus 1. So we can say something like the following. Assume that the statement holds for some n greater than or equal to 1. So we need to consider any n here in the whole problem, any n that we're trying to prove using the induction. So this has to work for any n greater than or equal to 1, i.e., we're assuming that 1 plus 2 plus etc. plus up to n is equal to n times n plus 1 over 2. Now we want to prove that the statement holds. We want to prove that our result holds for n plus 1. We want to show, let me make a note here off to the side. We usually wouldn't write this down in the proof itself, but we want to show that 1 plus 2 plus blah 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 plus n plus 1 equals n plus 1 times n plus 1 plus 1 all over 2. We want to show that if we know the result holds for n, then it holds for n plus 1. And this can take some experimentation. You might have to play around with this a little bit. What works in this case is what happens with many proofs by induction here. So we can take 1 plus 2 plus dot dot dot, and I'm going to take it up to n plus 1, but I'm actually going to write down the previous n as well. So what we can do is use the inductive by the inductive hypothesis. The inductive hypothesis is this assumption right here. We're assuming that 1 plus 2 plus da 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 up to n is equal to n times n plus 1 over 2. But that means that when we write down the sum 1 plus 2 blah 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 up to n plus 1, we've got a 1 plus 2 plus etc. up to n, and we have assumed that we know the result for n. So in fact, we've assumed that we know that 1 plus 2 plus blah 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 up to n is n times n plus 1 over 2. So if we take all the numbers up to n plus 1 by our hypothesis, that's n times n plus 1 over 2 plus another n plus 1, and now we can just start doing some math here. So if we expand things out a little bit, this is the n squared plus n over 2 plus, and now on the right term, we can give it a denominator of 2 by multiplying 2 on the top as well. So we get n squared plus n plus 2n plus 2 all over 2. This is equal to n squared plus 3n plus 2 over 2, which is in fact equal to n plus 1 times n plus 2. Let me n plus 1 times n plus 2 all over 2. Which is, in fact, note, exactly what we wanted. So we can finish it off by saying, thus, the statement holds for n plus 1. So by induction, it holds for all n greater than or equal to 1. Sorry, I'm getting a little crowded down here. So this is the way a typical proof by induction will work. Now, as I said, this doesn't match up precisely with the form that we saw in the axiom, because the axiom was talking about like this set S. So what's going on here in the background, which you can make explicit if you like, it's just not commonly done. We're letting S be the set of all numbers n such that 1 plus 2 plus up to n is equal to n times n plus 1 over 2. We're letting S be the set of all numbers that satisfy the condition that we want. In this case, making the equation true. So that's what we're doing. That's what we're doing in the background. We're letting S do this, then the base case is showing that 1 belongs to S. And then what the inductive step is doing is showing that if n is in S, that is, if 1 plus 2, etc., up to n is n plus times n plus 1 over 2, then n plus 1 belongs to S. Then n plus 1 satisfies the condition that we like, that we're looking for. So that's what's going on in the background of a typical proof by induction. However, in some cases, we will want to make the set S explicit, and when we do that, we can follow the axiom exactly. All right, now next I want to talk about a stronger form. Well, it's not really stronger, but it's called strong mathematical induction. And it's a version of induction that that uses a slightly different setup. We're going to start off the same way, though. So we want to let S be a set of integers if the following two things happen. The first one's the same. We want to say that if there's some number that belongs to S, and part 2 says for every n greater than A, if K is in S for all K that lie between A and N, then N is in S. So if S satisfies these two conditions, the conclusion is the same. Then S contains all integers greater than or equal to A. So let's look at what's the same and what's different about the principle of strong mathematical induction. First of all, I want to say that strong mathematical induction is actually equivalent to ordinary, standard mathematical induction. It's the same. If you have one, you can prove the other. It's called strong mathematical induction because of the difference in the way the inductive step is written down. But that's the only thing that's different. We're still starting with a set of integers. We still have a base case where we have to show that some number belongs to S. The conclusion's the same. The conclusion is still that S contains all integers greater than or equal to some number. And what's different is how we have to construct the inductive step. So for the inductive step, what we have to show now is that if we take some number bigger than A, and all of the numbers, all of the integers between A and N, but not including N, if all of those belong to S, then N belongs to S as well. So it looks like it's using a lot more than the previous form, because instead of just looking from one number to the next, we're looking from a whole bunch of numbers to the next number that's larger than the largest one of those. So we're looking at an n, and we're looking at all of the numbers less than it. And this form of mathematical induction is not used all the time, but it is very helpful when the thing that you want to prove doesn't have a natural progression from one number to the next. The last example that we did was very, very natural to use under the standard mathematical induction, because we're talking about adding up a bunch of numbers, and if we move from n to n plus 1, well, then we're literally just adding another number onto that, and so it made a lot of sense. However, there are some things that we can prove using strong mathematical induction that it's not at all clear how to prove it using standard mathematical induction. So let's see an example of that. Let's prove that every integer greater than 2, greater than or equal to 2, can be written as the product of prime numbers. So this is something that can be done by induction, but we really sort of need the strong form of it. Let's go and see how that goes. Let's look at the base case. Now in this case, the smallest number that we're looking at is 2, because we're only trying to prove a statement about all numbers greater than or equal to 2 here, so 2 is our base case. So we note that 2 is a prime number. Hence, it is a product of prime numbers. Namely, it's a product of a single prime number, just itself. So the base case holds. Don't actually write that down as part of the proof, but the base case holds here. So now we go to the inductive step. And as a quick aside, here's where ordinary induction won't work. So let's say, for instance, that you know that n is a product of prime numbers. It's the product of p1 times p2 times p3 up to p7, say, and is a product of 7 prime numbers. But then what's n plus 1? The fact is there's not a lot of relationship between the prime factorization of n and the prime factorization of n plus 1. At least not anything simple. I mean, n plus 1 could be a prime number, even though n is very much not, has a lot of prime factors. So ordinary induction doesn't really do anything for us here. Because there's no natural way of going from the prime factorization of one number to the number one more than it. So for this one, we're going to use strong induction. All right, so for that, we want to start off by saying, let's let n be greater than 2. And we're going to try and let n be greater than 2 and assume, here's our new inductive step, that every integer k with k lying between 2 and n, not including n, can be written as a product of prime numbers. So then we can look at n and we want to say, well, can n be written as a product of prime numbers? So we can look at n and we can consider 2 cases. If n has no factors other than 1 and n, then n is a prime number. So, so in that case, n is a product of prime numbers. All right, so that's one possibility. Here, for that one, we didn't even really need the inductive step. But then we can consider the other case. If n has a factor other than 1 and n, then we can write n as a times b, where a and b are both greater than 2 and less than n. So if n has factors other than 1 and itself, then that means that it has some factor that's bigger than 1 and say a, and then that a has to multiply by something else that's bigger than 1 but less than n. So we can write n is equal to a times b, where a and b are greater than or equal to 2 and less than n. But this means that now we can use our inductive hypothesis. So by the inductive hypothesis, a is equal to some product of prime numbers. Say r of them. Our inductive hypothesis is that every integer k with k between 2 and n can be written as a product of prime numbers. So by the inductive hypothesis, a is equal to p1 through pr, and b is equal to, I'll call them q1 through qs, where the pi and the qi are prime numbers. Thus, that means that n, which is a times b, is equal to p1 times p2 up to pr times q1 times q2 up to qs. So n is a product of prime numbers. And that's it. That proves the inductive step. So this shows that any number can be written as a product, any integer greater than 2, we need to be precise, can be written as a product of prime numbers. So this is the power of strong mathematical induction that we will sometimes use. Now, there is a related result. This exercise, that every integer greater than or equal to 2 can be written as the product of prime numbers, but we can do a little bit more work, and if you work a little bit harder at that, you get to Theorem 10, known as the fundamental theorem of arithmetic, which says that every integer greater than 1 is a product of prime numbers. That's what we just proved. And the product is unique up to reordering of terms. Of factors, I should say. So this says that when we go to a factorization of a number, like let's say we've got 60, and 60 is equal to 2 times 2 times 3 times 5. That's a factorization of 60 into prime numbers. And this factorization is unique. There's no other way of multiplying prime numbers together to get 60 unless you just reorder these. That's what up to reordering of the factors means. So we could also write this as 3 times 2 times 5 times 2, and occasionally you might want to consider that a different factorization, but except for reordering the factors, this decomposition into prime numbers is unique. So any prime factorization of 60 is going to involve 2 2s, 1 3, and 1 5 in some order. In particular, there are no other prime numbers that will ever show up, and you'll always have exactly these 4, counting the repeated 2. So this is one that that many of us are familiar with already from various places, and winds up being very useful even in advanced mathematics. So we'll be coming back to this before too long. All right, so next I want to start talking about the division algorithm. And this term here is not perfectly well matched to the form that we're going to be doing it in. We're not going to be talking about an algorithm per se, but it's the traditional name associated to this idea that we're about to do. In order to start talking about it, though, we need another fact. Theorem 11, which we're not going to prove here, but you can prove using induction that we just talked about. It's called the well-ordering principle. And it says that if S is a set of integers and S has a lower bound, then S has a minimum element, denoted min S. Now the lower bound here, what this means for S to have a lower bound is that there exists some integer n such that n is less than or equal to x for all x in S. So there's some integer that's less than or equal to everything in S. And as long as your set S has some lower bound, then it has a minimum element. Now, this may seem sort of trivial at first until you note that the real numbers do not have this property. So this is, in fact, something special about the integers and the ordering that we have on it. Not every ordering on a set, not every ordered set has this property. Not every ordered set is well ordered. So we note that this doesn't hold over R, for instance. So, for instance, the set 0, 1, the interval 0, 1 has a lower bound. It has many lower bounds, but it has a lower bound of 0, for instance. 0 is less than or equal to anything in this set S, but S doesn't have a minimum element. And that's because a minimum element of a set is required to actually be an element of that set. Now, if you've been in other classes, advanced calculus, analysis, things like this, you might point out that S has an infimum of 0, and you'd be right, but an infimum and a minimum can be different. Or if a set doesn't have a minimum, it might still have an infimum. But the well-ordering principle for the integers says that you're always going to get a minimum if your set is bounded below at all. So let's see how this is going to help us out. We can look at the following theorem. Theorem 12, known as the division algorithm. And it has to do with the structure of numbers and, or integers rather, and what happens when you try to divide them. This is actually quite a bit related to the concepts of modular arithmetic that we talked about, or not modular arithmetic, but congruence modulo a number that we talked about in the last lecture. So Theorem 12, the division algorithm, says let A and B be integers and be positive. So there exist unique Q and R. So remember that this notation, there exists with an exclamation point, is there exists unique Q and R integers with R between 0 and B, not including B. And this is the real key to it, is this restriction on R, such that A equals BQ plus R. The number Q is the quotient of A and B, and R is the remainder of A and B. We're not going to go through this proof completely. I want to do a few things to look at it. First of all, some visual intuition for why this makes sense, and it really can be a pretty natural thing to look at here. So one way that we can think about what we're doing is the following. We can imagine splitting up the number line in the following way. We can note all the multiples of B. On the number line here. And now I can choose A, and A has to appear somewhere on this number line. So let's suppose that A appears right there. And now visually, how do we find Q and R? Well, Q measures which one of these intervals between multiples of B your A belongs to, including the left-hand one and not including the right-hand one. So, for instance, this interval from 0 to B corresponds to all of the numbers where Q is equal to 0. From B to 2B, this is where Q is equal to 1, Q is equal to 2, Q is equal to 3, Q is equal to -1, and so forth. So, because A lies here in this interval between 2B and 3B, that means that A is going to be equal to 2B plus something. Now, how do we find the something? Well, that's the difference here between A and 2B, and that's going to be what our R is. So A in this case is going to be 2B plus R. And you can notice that wherever I choose to put an A on the number line, I'm always going to be able to break things up this way. Essentially what I do to figure out my Q is I move to the left on the number line from A until I get to a multiple of B. And then whatever multiple of B that is, that tells me what my quotient is. And then however much I have to go back up from that, or in other words, however far I had to go down in order to get to a multiple of B, is my remainder R. And so because R is always going just from a multiple of B to something in that interval, from 2B to, say, 3B, it's always going to be less than B. It never gets to be more than B. So this is sort of a visual way of understanding what the division algorithm says, claims about the structure of numbers, which is quite useful. The question then is, all right, well, how do we actually prove this? This is a very compelling image that we have here, and we might be able to make that explicit, and we can. As I said, we're not going to go through the proof completely, but I'll give the first couple of steps. So proof of the division algorithm. So we want to let S be a set, and it's going to be the set of all A minus BK, where K belongs to Z, and A minus BK is greater than or equal to 0. So what this is doing is something similar to the picture that I was just showing, except in a slightly sort of the opposite way. So what's going on here is we've got 0, and for the sake of this example, we'll imagine that A is positive. And then what we're doing with this value S is we're saying, all right, well, let's take A and subtract B times K, with K being an integer. So we could have A minus B, A minus 2B, A minus 3B, but then let's imagine A minus 4B would have been negative, so that means we don't include it, because this this set tells us that we're only including the A minus BK values, which are non-negative. Well, notice then that if we were to jump that all that way, then we'd have this gap here, and this basically tells us how much further we would have to go after subtracting 3 B's in order to get down to 0. Well, this value is going to exactly be our R. So the way that this cartoon is set up, we've got that A, in this case, is equal to 3B plus R. So we're going to let S be this set, the set of all the things that you get when you subtract B's a bunch of times, and we're going to let R be the minimum of S. So then we have to show a couple of things. We have to show, first of all, that R really is greater than or equal to 0 and less than B. So we need to show that R lies between 0 and B. Well, the first part is just by definition. So by definition, every element of S is greater than or equal to 0. So R is certainly going to be greater than or equal to 0. And then to show that it's less than or equal to B, we can use a proof by contradiction. So let's suppose that R is greater than or equal to B. And that R is equal to A minus B times some particular K1. But now, if R is greater than or equal to B, that means that R minus B is greater than or equal to 0, and R minus B is A minus B times K1 minus B. So that would be A minus B times K1 plus 1. But that means that this number right here, A minus B times K1 plus 1, is an element of S, because it's A minus B times some integer, and it's greater than or equal to 0. But R minus B is less than R, which is the minimum of S, a contradiction. So if R was greater than or equal to B, then it wouldn't be the minimum of S, but that's how we defined it in the first place. So that can't work. So therefore, R is in the interval that we want, between 0 and B, not including B. And so this means that A is equal to this K1B plus R that we had, and this K1 is the Q that we wanted from the division algorithm. Now, notice that we're not done yet. We still have to show uniqueness, and the uniqueness proof is in the notes. Definitely make sure to read through that, because the uniqueness claim is something that you actually have to work out. So we showed that there is a way of writing down A as some integer times B plus some other integer, R, where R is small. And then we show that it's the unique way of doing that which proves the division algorithm. The division algorithm is essential to proving the next theorem, which has to do with greatest common divisors. So let's start with a proof of those, or definition of those, rather. So definition 13, let A and B be in Z, the integers, not both 0. One of them can be 0, but not both of them. The greatest common divisor of A and B is, first of all, it's denoted GCD AB for greatest common divisor. The largest integer D such that D divides A and D divides B. So the name for this is very descriptive. The greatest common divisor. It's the greatest number which is a divisor of A and a divisor of B at the same time. If the greatest common divisor of A and B is 1, that is, if they have no divisors in common other than 1, or greater than 1, then A and B are called relatively prime. There are lots of examples, and this is not something that is going to be new to very many people. But if I look at the numbers 18 and 20, let me if I look at the greatest common divisor of 18 and 20, well, what I can do is I can start looking at numbers and going up and seeing, all right, do they divide 18? Do they divide 20? Possibly a simpler way of doing it in general is to factor using the factorization into prime numbers that we talked about just a little bit ago. So 18 is equal to 2 times 3 squared. 20 is equal to 2 squared times 5. And what you may remember from previous courses is that you can find the greatest common divisor or the greatest common factor of two numbers by factoring them into primes, and then for each prime choosing the lowest power of that prime that appears in either of the factorizations. So in this case, you'll notice that the only factor they have in common is 2, and 2 only goes into 18 once, and so the greatest common divisor of these two is just 2. The greatest common divisor of 18 and 21 is equal to 3. And then the greatest common divisor of, let's say, 50 and 51 turns out to be 1. So we would say that 50 and 51 are relatively prime, even though neither one of them is a prime number. Just a few examples there. What's amazing about the greatest common divisor, though, is that it can be described in a different way that's very, very useful to us. So that's Theorem 14. So let's let a and b be integers, not both 0. The greatest common divisor of a and b is equal to the minimum of the following set. It's the minimum of all numbers of the form a times s plus b times t, where s and t are integers, and where as plus bt is greater than or equal to 0. So it's the minimum of all positive combinations of these two numbers that you could get. If you look at all the different ways that you could take some integer times a plus some integer times b, look at all the different combinations of those that you could get, and pick the smallest positive one. Oh, yes, I shouldn't have written greater than or equal to 0. They need to be strictly greater than 0. If you take the smallest strictly positive one, that will be the greatest common divisor of these two numbers. And that's really sort of exciting. How do we do this? Well, let's look at the proof. So we could go about this a couple of different ways. We could first try to start with the greatest common divisor, and then try to prove that you could write it as a combination of a and b, as as plus bt of some way, and then try to argue that it's the minimum one. That turns out to be a pretty difficult way of approaching it. It's going to make it easier for us to start with the minimum of the set on the right, and then prove that it's the greatest common divisor of a and b. So let's let d be the minimum of all numbers, the set of all numbers as plus bt, where s and t are integers, and as plus bt is positive. There exist a specific s and t in Z such that d is equal to as plus bt, because every element of the set looks like this, and D belongs to that set. And now we're going to use the division algorithm. So by the division algorithm, what we're going to do is we're going to divide A by D. We're trying to show that D is a common divisor. And one way of doing that is to show that when you use the division algorithm, R has to be 0. If we can show that R is 0, then that will mean that A is actually equal to Q times D, which will mean that D is a divisor of A. So by the division algorithm, A is equal to QD plus R for some Q and R in Z with R between 0 and D. So we would like for R to be, we would like to show that R is 0, because that would show that D is a divisor of A. So let's try and write down what R is. So therefore, R is equal to, well, if we just solve this equation, it's A minus QD. But we know what D is. D is AS plus BT. Now, if we rearrange this a little bit, what we get is A times 1 minus QS plus B times negative QT. Now, here's where we need to notice that this is the type of thing that shows up in the set that we're talking about. Which I should probably give a name. I should stop calling it just the set. We'll call this set capital S. So this suggests that R belongs to S if R is positive, because remember, S only includes positive things. So if R was greater than 0, then R belongs to S. But we also know that R is less than D, which is the minimum of S. A contradiction. So this means that R is not greater than 0, but R was only allowed to be between 0 and D. So since R is not greater than 0, R has to be equal to 0. So therefore R is equal to 0, and so A is equal to QD, that is, D divides A. So we have that D is a divisor of A. Okay, so now what about B? We could go through this whole process again. However, you'll notice that there's nothing really special about A in what we did. And if we replace all of our A's by B's in the argument that we just made, then we get almost exactly the same thing, and we do in fact get to the same conclusion. So we can say by a similar argument, D divides B. Thus, D is a common divisor of A and B. All right, so that's good. We're almost all the way there, but not quite, because we need to show that D is the greatest common divisor. And we've only shown that it's a common divisor, that that D divides A and B, but we haven't shown that there isn't something else that that's bigger than D that also divides both A and B. So let's go to that. So now let's let D prime be another divisor of A and B. So we have that D prime times, let's say M is equal to A, and D prime N is equal to B for some integer N. So let's see how this relates to D. We have that D, we still know that D is equal to AS plus BT for this particular S and T that we chose at the beginning. But AS plus BT is now D prime M times S plus D prime N times T. So this means that D is equal to D prime times MS plus NT. Therefore, D prime divides D. And since D is positive, if you have some number that divides a positive number, that means it must be less than it. But since D is positive, D prime is less than or equal to D. So D is not only a common factor, a common divisor of A and B, it's the greatest common divisor of A and B. Therefore, D is the greatest common divisor of A and B. And so that's how we can use things like the well-ordering principle, which gave us a minimum, which relies on mathematical induction to do things in the first place, in order to show how the greatest common divisor always has a very special form. Finding the specific ways to write down the greatest common divisor can be difficult in some cases and easy in others. So let's look at an example. Let's look at the numbers 12 and 20. The greatest common divisor of 12 and 20 is going to be, well, let's see, 12 is 2 squared times 3, 20 is 2 squared times 5. So the greatest common divisor of the two of them is going to be 4. Now, by the theorem, there should be some way of writing 4 as 12 times something plus 20 times something. Now, of course, this is going to involve some positives and some negatives. And you can do some experimenting around with it. There are algorithms that can actually get you to that point. And if anyone's interested, I'm happy to send you in the direction of such algorithms. We won't be using them so much in this course, but we've got 4 is 12s plus 20t for some s and t. And so, for instance, we could use 4 is equal to 12 times 2 plus 20 times negative 1. This is something that will work. So 12 times 2 is 24. 20 times negative 1 is negative 20. And so the two of them together add up to 4. And in fact, it's not possible to get 12 and 20 to combine together to give you anything less than 4. Now, this is not the only way of doing it. We could also have 4 is equal to 12 times 7 plus 20 times negative 4. Yes, that one also works. In fact, there are infinitely many ways of describing the greatest common divisor of two numbers as a an integer combination of those numbers.